Welcome to this session of Finite Element method. In this session, I will going to discuss about stress and equilibrium, my dear students. Now, consider there is a coordinate axis. Here it is x, y, z. There is a three-dimensional object here. All of you see, there is a three-dimensional object. So, a part of the boundary is fixed here. So, other part of the boundary, it is applied to traction force. So that it is subjected to traction force, my dear students. What is a traction force? Traction force is nothing but, suppose if it is a surface per unit area. What is a distributed force per unit area? That is called as a traction force, my dear students. Now, coming to consider from this 3D, we are consider a small elemental volume. Small elemental volume. For that volume is dV. So again there is a body force. Here is this body force is represented by the letter F. What is a body force, my dear students? For example, it is a three-dimensional object. It is a three-dimensional object. So what is a distributed force per unit volume? That is called as a body force, my dear students. For this per 1 unit volume in x direction, the body force is Fx. For dV volume, we are multiplied with Fx into dV. Okay, again similar fashion, the body force in x direction per unit volume is Fy. For dV volume, Fy multiplied with dV. Similarly, body force in z direction, that is Fz per unit volume. So total body force in z direction Fz into dV, my dear students. Yes or no? So because when traction force is applied, because of that there is a deformation takes place in x direction. That is, deformation x direction is u, deformation y direction is v, deformation z direction is w, my dear students. Because of the force, the stresses are induced in this member. Yes or no, my dear friends? Now coming to here, I will write down each and everything, don't worry. Here is the first of all, what is a traction force? Traction force. It is represented by the letter T. So distributed force per unit surface area. Per unit surface area is called traction force. Traction force, my dear students. Here is what is the example for this traction force? Example for this traction force is distributed contacted force. Distributed contact force. Distributed contact force and action of pressure. Action of pressure, my dear students. So the traction force, a part of the boundary, we are applying traction force. So that because of that force, there are three components, that is traction force x direction, that is perpendicular to my screen, traction force y direction, traction force z direction. That is the traction force and its components, that is Tx, Ty, Tz whole power transpose. So Tx is nothing but traction force in x direction, Ty is nothing but traction force in y direction, Tz is nothing but traction force in z direction. Now coming to body force. What is a body force, my dear student? It is represented by the letter F. So distributed force per unit volume. Per unit volume. So is called body force. body force. Here is what is the example for this body force, my dear students. Example for this body force is weight per unit volume. Weight per unit volume. Weight per unit volume. The body force is represented by the letter F. So the components of body force is given by Fx, comma, Fy, that is body force x direction, Fx, body force y direction, Fy, body force z direction, Fz, whole power transpose. See, my dear students, what is meant by equilibrium? Here is our concept is stress and equilibrium. What is equilibrium? Algebraic sum of a body is said to be in equilibrium condition. Algebraic sum of forces in x-axis direction is equals to 0. Algebraic sum of forces in y-axis direction is equals to 0. Algebraic sum of forces in z-axis direction is equals to 0. At that time, the body is said to be in equilibrium condition. So, that is sigma Fx is equals to 0, sigma Fy is equals to 0, sigma Fz is equals to 0. All of it clear, my dear students. Now, coming to when force is traction force, we are for calculating equilibrium, we are considering traction force and body force only, my dear students. Because of the force, stresses are induced in this elemental volume dV. This is the elemental volume. For this, width is dx, length is dy, length of the elemental volume is dy, height of the elemental volume is dz. Okay. Now, it is consider it is x-axis, it is y-axis, it is z-axis, my dear students. So, now the stress in, so all of you carefully observe, this is A, here is B, here is C, here is D, here this corner is E, F, G, H. Now, B, F, G, C. This B, F, G, C, this is called as positive X phase. Positive X phase, my dear students. Again, A, E, this is E. A, E, H, D. A, E, H, D. A, E, H, D. This is called as negative X phase. Negative X phase, my dear students. All of you carefully listen here. Suppose, for example, there is a small elemental volume. I am taking only one plane. I am applying stress. Here is sigma x. For this length of this plane is equals to dx. What is the stress on this face? Okay, but somewhat here is somewhat higher than this or somewhat lower than this, we don't know. But how to find out this one? Here is stress on this face is sigma x. When it passing through the distance dx, there is a change in stress that must be either increasing manner or decreasing manner. How to find out that change? That change can be find out by dou x of sigma x. This stress passing through the distance, this is a change. Either it is a positive or negative. But at this phase is sigma x. Sigma x plus change in this plane is equals to stress at this point. That is, I am assuming that it is a sigma x plus. So now sigma x plus is equals to stress on this phase plus change of the stress when passing through this plane, that is dou x of sigma x. It is per unit distance for dx distance into dx. It is a very important. All of it clear, my dear students. So per unit distance dou x of sigma x for dx distance into dx plus this sigma x. This may be either positive or negative, either increasing manner or in decreasing manner, whatever it may be. So now coming to here also, so now I am consider it is a positive x phase. It is a positive x phase. It is a negative x phase. It is a positive x phase, my dear students. So this is a negative x phase. B, F, G, C is a positive x phase. So A, E, H, D, it is a negative x phase. Now coming to, because when stress is on this phase, this stress is sigma x plus, because it is acting on positive x phase, my dear students. It is a positive x phase, so that, but it is acting perpendicular to the surface, so that it is a normal stress. Now there is another stress is here. This is a stress. Now it is parallel to this positive x phase. When it is parallel to the positive phase, that is called as a shear stress. But it is in x phase, but which direction? Y direction, tau xy, but it is on positive x phase, tau xy plus. Similarly, there is a stress is here. This stress is parallel to this phase, but when stress is parallel to this phase, this stress is called as a shear stress, but it is in x plane but z direction, but it is on positive x axis, so that it is a positive. Excellent, my dear students. Now I will use a different color for negative x phase. Now coming to negative x phase, AEHD, this is a negative x phase, my dear students. This stress is perpendicular to the negative x phase, so that this is a normal stress. For representation of negative stresses, only sigma x, tau x, like that only. So here it is a perpendicular to this phase, so that it is a normal stress. Now coming to this one, this is parallel to this phase. Now it is a shear stress, but it is in x phase, and which direction, my dear students? Y direction. So similarly here also it is parallel to x phase, my dear students. So it is also shear stress tau, but it is in x phase, which direction? Z direction. Excellent, my dear students. Now coming to, here is phase, stress on negative phase, stress on positive phase. Now coming to here, phase, this is x phase, this is where consider x phase. So negative phase, normal stress on negative phase is sigma x. What is the normal stress on positive x phase? That is sigma x plus is equals to sigma x plus. When it is passing through this distance, there is a change in the stress. There is a change in the stress per unit distance, that is dou by dou x of sigma x. For dx distance, it is into dx. Okay. Now consider, here is a shear stress tau xy. So negative phase, the shear stress is tau xy. Similar fashion. So that is tau xy plus is equals to tau xy plus, this is x, dou by dou x of tau xy into dx. Again similarly tau xz. So that is a shear stress on negative phase, tau xz. Here is tau xz plus is equals to tau xz plus change when it passing through this dx distance. Per unit distance, change is dou by dou x of tau xz. For dx distance, dou by dou x of tau xz into dx. Dou by dou x of tau xz into dx. Excellent, my dear student. Now coming to y phase. Now this is x axis, this is y axis, this is z axis, my dear students. Now coming to x phase. Now here is, what is this? A, B, C, D. Here is E, F, G, H. Here is this phase. What is negative y phase? Here is now it is a distance. All of you see, my dear student. It is a distance of dy. This phase E, F, G, H. It is a distance of dy. So that it is a positive y phase. It is a positive y phase. A, B, C, D. A, B, C, D. It is a negative y phase, my dear students. It is a negative y phase. Now here is E, F, G, H. It is a positive y phase. It is a positive y phase. Again, A, B, C, D. It is a negative y phase, my dear students. Negative y phase. Now, in this direction, it is perpendicular to the positive y phase, so that this is sigma y plus. It is a normal stress in positive y phase, so we will call it as a positive. We call it as a positive here. So now here, this stress is a parallel to this positive y phase, so that it is a shear stress, but it is in y plane z direction, tau yz. Now coming to here, again there is a stress. This stress is parallel to this phase, so this is a shear stress, but it is in x plane. Which direction? So sorry, y plane. Y plane. Which direction? X direction. Excellent, my dear student. Because all these are present in positive y axis. This is tau yz plus tau yx plus. Now coming to here. So I will use a different color for this clarity purpose. Now here is a stress on negative y phase. This is a normal stress. It is acting perpendicular to the negative phase, so that it is a sigma y. All of it clear, my dear students? Now coming to here, this stress is parallel to this negative phase, so it is called as which phase? It is in y phase. It is in y phase. Which direction? Z direction. All of it clear. Again, this is a shear stress because it is parallel to this phase. Tau, it is on y phase. Which direction? X direction. Tau yx. Yes. Now here is phase. Stress on negative phase. Stress on positive phase. So whatever the procedure is followed for X phase, same procedure is applied here also. This phase is Y. So here is sigma Y. Negative phase, the normal stress is sigma Y. What is the sigma Y plus? That is equals to sigma Y plus. When it is passing through the dy distance, that is sigma y plus dou by dou y of sigma y into dy. Yes. Again, what is the shear stress? Tau yx on negative y phase. So what is the positive y phase? Tau yx plus is equals to tau yx plus dou by dou y of tau yx into dy. So next one, tau yz, that is shear stress on negative phase. What is a tau yz plus? That is equals to tau yz plus dou by dou y of tau yz into dy. All of it clear? Similar fashion, now coming to z phase. Now it is a x axis, now it is a y axis, now it is z axis. Now it is Z axis, my dear students. Now here is A, B, C, D, here is E, F, G, H. All of you see, my dear students, this phase A, B, F, E, A, B, F, E. This is a positive Z phase because it is at a distance of dz from the origin. So this is a positive Z phase. Now it is a negative Z phase. It is a negative Z phase. What is the negative Z phase here? DC, DCGH. It is a negative Z phase, my dear students. Excellent. Now, on positive Y phase, it is a normal stress. This is normal stress, my dear students. Tau Z plus. Again, coming to here. This is on Z plus phase, so that it is a parallel to this Z phase, so it is a shear stress. But it is in Z phase, which direction? Y direction. But it is on positive Y, positive Z phase, it is a positive. Now coming to this one. What is this? It is on Z phase, shear stress, because it is parallel to this phase, shear stress. Tau Z, which direction? X direction. But it is on positive Z phase, that is a tau Z plus. Similarly, here also. So I will use different color for this, for our clarification purpose. Now here is the stress in this direction. This is sigma Z. It is a stress on negative phase. Now coming to this is a stress. It is parallel, so that it is a shear stress on negative Z phase. Which direction? Y direction. Now similarly, again there is a stress is here. It is parallel to Z phase. It is a shear stress tau. But it is on Z plane. Which direction? X direction. Okay. All of you clear, my dear students? So again, similar procedure. Phase, stress on negative phase, stress on positive phase. Okay. Now here is phase is Z. Phase is Z, my dear students. What is the stress on negative phase? This is a negative Z phase, sigma Z. So what is the stress on positive Z phase? Sigma Z plus is equals to sigma Z plus. So when it passing through the dz distance, there is a change per unit distance is dou by dou Z of sigma Z. For dz distance, dou by dou Z of sigma Z into dz. So dou by dou Z of sigma Z into dz. So what is another stress? That is so here is a tau zx, that is on negative phase. What is the stress on positive phase? Tau zx plus. Tau zx plus, that is equals to tau zx plus dou by dou Z of tau zx into, sorry, here is dz. Here is dz, sorry. So into dz. Per unit distance, dou by dou Z of sigma Z into dz. So again, for dz into, for dz distance multiplied with dz. Now similarly here also, what is a tau zy? That is tau zy plus, that is equal to tau zy plus dou by dou Z of tau zy into dz. All of you clear, my dear students? Yes or no? So see, here is, I am writing all in one place. So now it is, this is x axis direction, this is y axis direction, this is z axis direction. So here is on this face, this is sigma x, this one is, so this one is tau x face y direction, that is plus, here is this is tau x face z direction plus, okay. Now I am writing only positive faces, stresses on positive faces only. Now this is sigma x plus, now this is sigma y plus. Now stress in this phase, that is tau y z, this is plus, here is tau y x plus, this is sigma z plus. So here it is tau z y plus, this one is tau z x plus. Now first of all consider algebraic sum of forces x direction is equals to 0. What are the forces in x direction? This is one force. I will use a different color for this. So x direction forces are, here is a sigma x, here is the width of the elemental volume is dx, length of the elemental volume is dy, height of the elemental volume is dz. Yes. What are the forces in x-axis direction? This is a stress into this surface area is called as force. This is x-axis direction. This is also x-axis direction. This is also x-axis direction. Now that is, so the net force acting in x-axis direction is equal to sigma x plus, what is this face, what is the area of this face? Dy into dz, dy into dz minus of, so this side, this is sigma x minus negative face sigma x into dy dz. This is net force x direction plus, again there is another shear force term is there, it is also x direction. Now tau y x plus, on which face it is acting? Dx dz, dx dz. Again on this face it is a negative, that is tau y x dx dz plus. So here is, again there is another one is tau z x plus, and it is acting on surface on this face dx, what is the area? Dx dy minus of tau zx into dx dy. So this is a first term, I am called as first term. It is a second term. Here is a first term, my dear students. It is a second term, my dear students. Here it is a third term. I am solving all these terms. We are finding the equilibrium equation in x direction.